Hey everybody, welcome to Madden Science. This is Populations Part 2, so another flipped classroom lesson. If you didn't get to check out Population Part 1, I'll probably go ahead and do that right now before you check out this video. Alright, flipped classroom lessons. You can read through it. A specific point to highlight is number 6. Make sure you're adding a comment down below that deals with something interesting, fascinating, specific in this talk, and tie it to a specific time. So lots of examples that I'll use throughout. I'd like you to add one more. I look forward to reading what you got. All right, we just covered pretty much the beginnings of Unit 3 on populations, kind of the non-human specific parts. We did touch on survivorship curves. We're going to hit the other sections in this video. So here we are again, hanging out with populations in between organisms and communities. Here is a unit at a glance, so just some redos on the slides here. Good time to check off these, like how did you do in video 1? How'd you do with checking in with your book and your notes? When you're done with this video, come back to it. We should be pretty solid on 3, 1, and 2, 3, 4, 5. Okay, so those sections, the first 5, you should be solid on after watching these videos. And I need you to ask some questions too. So the part of being able to do these flipped classroom lessons is that we can devote time in class to your questions and activities and labs. All right, 3, 4, we'll start with carrying capacity. 3, 5 with population growth. So those two kind of are merged together. So exponential growth seen here. So you're going to have this early lag phase. So we're outlining it, highlighted in purple, as it comes up in and along here. So this exponential J curve, you saw it with human populations, right? What we want to note is really kind of this tangential piece. So a tangent to this line is getting steeper and steeper. So if you have a number in a population in time, you have its rate of growth. So on that curve, the slope is changing, and as you go along in time, the slope is getting steeper and steeper. Now it shows in here, in natural populations, they rarely continue forever at an exponential rate. Environmental factors pretty much always intervene, although humans haven't quite met that just yet, at least Homo sapiens. Logistic or S-shaped curve is named S-shape, again, because it is. So it's growing, increasing, slope goes up, and then at this point, you can see that the slope starts to decrease. So if you had a tangent right here, see that slope is shallower than it was down over here. So it gives you some explanations here. You also note the addition of the carrying capacity, which is shown right here in this dotted line along the middle. So that's going to be some number that is going to be determined by the environment, kind of as a cap, right? Beyond there, the population isn't going to be able to exist in equilibrium or in balance. So you say it encounters resistance to that growth. So there's going to be factors that we talk about that are pushing down on the ability of that population to continue growing. Again, think about the positives to population growth. Birth and immigration versus the negatives, death and emigration. Really, it's the birth and death that are factored, so you'd get a decrease in birth rate combined with perhaps increase in death rate, or one or the other. Now, an interesting rule that you can use to help with calculations is sometimes called the rule of 70. And it shows that you can do doubling time and percentage growth together with 70. So if you want to do, for instance, your town is growing by 2% every year, that means it'd double in every 35 years. So you get that by 70 divided by your percent growth. That works in the inverse way too, where you'd say US population is going to double in 70 years. Well, then you take 70 divided by your doubling time, or 70 divided by 70, which equals 1, or the growth would be 1%. Here's a view at two different exponential curves, so J curves, one with a rate of 1, one with a rate of 0.5. So population size divided by time. Currently, human population on Earth is around 1.2 for our rate of growth. Now imagine if you had bacteria growing as it normally might, say dividing, doubling through fission every 20 minutes. It'd only take 36 hours of uninterrupted growth to cover the entire Earth a foot deep. Now clearly that doesn't happen. Now why? Because there's competition, there's accumulation of waste, there's not enough resources for them to grow. Another interesting J-curve or exponential growth problem came from NPR that highlighted vampires, saying like, hey, are vampires real or not? They're saying they're not, because if they were, and if they were immortal, then eventually they would convert or change everybody into vampires, which means either there are no vampires or we're all vampires. I don't know. Another example of J-curve exponential growth is in Kruger National Park in South Africa. This ended up being problematic and still is. People looking at what to do with it, perhaps even culling those elephants. This shows us our S-shape or sigmoid curve or logistic curve again. You can see carrying capacity in this case at 1500. This is met with a real-life example here with paramecium. Sometimes organisms overshoot that, so the growth comes in here and goes above carrying capacity, which is, in this case, I don't know, right around 135 Daphnia per 50 milliliters. Now, Daphnia are commonly used in biology classes, maybe for investigating heart rate. They got a really cool dorsal heart that you can see beating boom, 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 super fast. It's also to say that sometimes you've got populations that fluctuate, in and around K. So it can go up and down below depending on years or seasonality. So what is it that helps populations regulate? So there's negative feedback in here, where as a population goes up, there are environmental factors that help curb or change or tame that growth. So two general groups: density independent and density dependent factors. So independent means these factors are going to be present no matter what the density of the population. So as density goes up, these factors remain the same, like rainfall or the amount of food, or a flood. In the case of density dependent factors, you can see them listed here. And so as the density goes up, the impact of these factors is going to strengthen. So you're going to have fewer food, more disease, more competition, more predation. And the changes that come about are going to be on the left, increase in mortality, which is lowercase m, or a decrease in natality or birth rate, which is lowercase b. And from our book, it shows some examples of limiting factors here that help stabilize this population. You can see that the slope of this curve begins to taper or decrease. All right, now if we look in on this, you can see population density increasing as we go from left to right. And in part A, both of these change with population density. So in the blue, you've got birth rate. So in part 1, as population goes up, birth rate goes down, and mortality rate goes up. In part 2, you got, as density goes up, death rate is density independent. So the death rate doesn't change, but the birth rate does go down. And then on the third example, you got density increasing, and in this case, the birth rate doesn't change, or it's independent, and the death rate or mortality goes up, seen here. So what are these environmental factors that contribute to curbing population growth or changing that slope? Well, here we go. We got density independent factors, so a few more from the slide we saw earlier. This is a slide from Biozone. So some are physical or abiotic. Again, they're going to be, as they are no matter what, the population density. And then catastrophic events will also be independent of density. Now, things that do depend on density, so density dependent factors, so as density increases, you're generally going to have a dwindling food supply, increase in disease, parasite infestation, competition, and predation. Some of these intrinsic factors of density-dependent regulation would include competition, disease, predation. So here they are with a slightly longer explanation in a picture, along with territoriality. Sometimes intrinsic factors that would be genetic. So as density goes up, they would naturally, instinctually decrease birth rate. And then also toxic waste. You can see some of those intrinsic factors coming into play here with plantains. So as the number of seeds per square meter goes up, you'll have a decrease in the productivity of those plantains. Similarly, for the density of females, as that goes up, you would have a decrease in the average clutch size. And toxic waste can also contribute. It's why you can get pretty much a max of 13% alcohol, say in wine, before needing to distill. Or here's a pretty funny far side. This also shows that in fact, many large mammals don't hang straight at an equilibrium around the carrying capacity, but do indeed fluctuate. This is from, if you remember, our Isle Royale with moose and wolves. Also here, it's kind of mimicking what you might see with an invertebrate such as a crab. You might get population boom and bust cycles. So say population of hares went up, right? That's more food for lynxes, so lynx population goes up. If there's more lynx, you might get fewer hares. Fewer hares, fewer lynx. Fewer lynx, more hares. More hares, more lynx. More lynx, fewer hares, fewer hares, fewer lynx. Fewer lynx, more hares. More hares, more lynx, and it goes on and on and on. Next, section 3.1. So back to really the beginning, we're closing with it. Generalists versus specialists. Reminds me of a book I'm reading, really cool, by David Epstein, called Range, on the importance of being a generalist in the world, in your thinking, in your academics, also in your sports, right? These days, too often kids are specializing early on. Don't do it. If you don't believe me, read this book. You got pandas with a very narrow and specific niche, including their diet of bamboo, versus raccoons that are generalist, able to adapt to most anything. Both are very cute. Here you can see that same spectrum, kind of like we saw earlier with survivorship curves. So these are labels that fit and work, but they also have a spectrum or degree. So it's not perfect for every organism in every case, every time. So you're looking at size of a niche, adaptability, likelihood of going extinct, use of resources, ability to adapt to changing conditions. This is just a diagram from Discover magazine showing pandas, raccoons, and then, Homo sapiens, maybe as a generalist specialist. So not just a jack of all trades, but a masterly jack of all trades. Then you got different integration of food webs on the right. This reminds of a slide from earlier in the year with winning and losing species, kind of a harsh way to put it, but maybe true, and generalists versus specialists. Hi, 3.2, K and R selected species. Another example of a definition population that applies to some but not all. You got your same, really combined in this case, J curve and S curve. In the case of R selected species, existing generally in and around this exponential growth phase versus K selected species hanging in here, in and around equilibrium of carrying capacity, hence K for carrying capacity, R for rate. So the rate or reproductive growth here, which you'd get a population divided by time. Article just from a few weeks ago in the New York Times on these marsupials dropped dead after mating. So a little red Kaluta It's pretty much the cutest guy in the world. The reproductive strategy is kind of sad. Here you can see a comparison of correlates for R and K selected species, noting that many species exist somewhere in between. Here's another diagram from Biozone to help us out, and then I broke it down. Fits pretty much like this. So this is a good place to pause. See our arrow or spectrum from right to left, covering number of offspring, parental care, reproductive maturity, size of offspring, how independent they are at birth, their ability to learn, lifespan, and mortality. All right, that's it. Coming up next, we're diving full into human population. Cool Nova site with World Imbalance. We'll dissect the most famous hockey stick or human population curve here. I guess maybe not most famous. Now we've got CO2 to join. All right, that's it. Make sure you put your comments down below, something specific and cool with a time stamp. Let me know if you have any other feedback. Take care, everybody.